Reciprocal Functions Lesson 1. We're going to focus on graphing a reciprocal function, analyzing the graph, comparing the graph of a function to the graph of its reciprocal, and identifying the values of x for which the reciprocal has vertical asymptotes. Remember that the product of a number and its reciprocal is always equal to 1. For example, 3/4 is the reciprocal of 4/3. And 4/3 is the reciprocal of 3/4 because 3 over 4 times 4 over 3 is equal to 1. So for any non-zero real number a, the reciprocal of a is 1 over a. And the reciprocal of 1 over a is a. So for a function, f of x, its reciprocal is going to be 1 over f of x, as long as f of x isn't 0. Let's compare the graph of a function and its reciprocal. Sketch the graph of y equals f of x and its reciprocal function, y equals 1 over f of x, where f of x is equal to x. So we want to start with our function y equals x. We want to see how it's related to the reciprocal function, where y is equal to 1 over x. So we're going to create a table of values. I'm going to do both tables at once. So I'm going to select values for x. I'm going to find the y value when my function is equal to x. And I'm going to find the y value when my function is equal to 1 over x. So let's start with negative 10. If x is negative 10, for our first function f of x, y is also 10. For this one, it would be 1 over negative 10. For negative 5, y equals x would also be negative 5, but y equals 1 over x would be 1 over negative 5. For negative 1, y equals x would also be negative 1, and y equals 1 over x would be 1 over negative 1, or just negative 1. What about if our x value is a fraction, like negative 1/2? Well, y equals x would also be negative 1/2, but its reciprocal would be negative 2. I'm going to extend these a bit. What if we have a y value or an x value of 0? Well, y equals x would also be 0, but y equals 1 over 0 is undefined, so this one would be undefined. Let's look at some positive values. Let's look at 1/2. Y equals x would also be 1/2, but y equals 1 over x would be the reciprocal of 1/2, or 2. If x is 1, y will be 1, and the reciprocal of 1 is 1 over 1, or 1. If x is 2, y equals x is 2, but the reciprocal will be 1/2. And let's do one more. If y is 5, x is 5, and the reciprocal is 1 over 5. Now let's plot those points and see what happens. If I start by graphing y equals x, I know that at 0 and 0 is a point. I know that negative 5, 1, 2, 3, 4, 5, and negative 5 is a point. I know that negative 10, and negative 10 is a point. So this is a graph of a straight line, and I could plot those other points. But y equals x is just a straight line like this. So this is our function y equals x. Let's look at y equals 1 over x. When x is negative 10, we look at this first point, our function is negative 1/10. So it is awfully close to 0, but not 0. If I come back to x equals negative 5, my y value is negative 1/5, so it's a little bit further away. I should use a different color for these. Let's make these in red. When x is equal to negative 1, y is also negative 1. When x is equal to negative 1/2, so halfway between 0 and 1, my y value is negative 2. If I look at 0 and 0, at an x value of 0, my y value is undefined. So that means that it will never, my reciprocal function will never reach the y-axis. If we had another point in here of negative 1/5, this would be negative 1/5, but this one would become negative 5. So negative 1/5 is close to 0, and we'd come all the way down to negative 5. So we can see that this part of our graph is shaped like this. Moving into positive values, y equals 1/2, the reciprocal is 2. Y equals 1 is 1. If x equals 2, then our y value is 1/2, and that same sort of pattern is occurring. So the graph in the red is our reciprocal function, the graph in the blue is our original function. The function y equals x is a function of degree 1, so its graph is a line. The function y equals 1 over x is a rational function. Its graph has two distinct pieces or branches. These branches are located either side of the vertical asymptote. Our vertical asymptote in this question is the y-axis. It's defined by the non-permissible values of the domain of the rational function. And the horizontal asymptote is designed by the fact that the value 0 is not in the range of the function. So this is my horizontal asymptote. So let's look at some characteristics of that function. Our domain for y equals x is negative infinity to positive infinity. For y equals 1 over x, it's the same thing with one exception. In this case, x cannot be equal to 0. Our range, so for y equals x, is again negative infinity to infinity. For y equals 1 over x, again very similar, negative infinity to infinity. However, we cannot have a y value of 0 because that's where our vertical asymptote was. We're going to look at something called end behavior. I'm going to go back to my graph for a minute. When x is very large and negative, so the further we move this way, let's look at what happens to y equals x. It gets very large and negative. As x gets very large and positive, our y equals x gets very large and positive. So let's fill that in. So when x gets large and negative, y gets large and negative. When x gets large and positive, y gets large and positive. Now let's look what happens to the reciprocal function. When we go this way and x gets large and negative, our reciprocal function, so our red line, gets closer and closer to 0, and it's approaching from the negative side. When x gets large and positive, so going this way, our red line gets closer and closer to 0 from the positive side. So filling that in, when x is large and negative, y approaches 0 from the negative side. When x is large and positive, y approaches 0 from the positive side. also important to note that there's a horizontal asymptote at y equals 0. We never reach that x-axis. So what happens when x is equal to 0? When x is equal to 0, y equals x is just equal to 0. So we end up with y equals 0. But our reciprocal becomes y equals 1 over 0, which is undefined. This gives us a vertical asymptote. Last of all, invariant points. Invariant points are those points that are common on both graphs. And so we have one here and one here. Those points occur at -1 and 1 and +1 and 1. So this is just some definitions, and I'm not going to read through them, talking about asymptotes, horizontal, and vertical. Example number 2. Graph the reciprocal of a linear function. So if our function is f of x equals 2x plus 5, first of all, we need to determine what the reciprocal function is. And this is very easy because it just becomes 1 over our original. So it becomes 1 over 2x plus 5. We want to determine the equation of the vertical asymptote. Well, the vertical asymptote happens when our denominator of our reciprocal function is equal to 0. So the denominator is 2x plus 5, and when it's equal to 0, we have a vertical asymptote. So solving this equation, we end up with 2x equals -5, or x equals -5 over 2. So this is our vertical asymptote. Part C, we're going to graph the function of y equals f of x and its reciprocal. So let's start by graphing y equals f of x. And I'm going to graph it in red because I've been doing all of my work so far in blue. So if we're graphing y equals f of x, and in this case that is 2x plus 5. Different ways that I can graph it. I can create a table of values. I can use my x and y intercepts, or I can use that y equals mx plus b. This means that my y-intercept is 5 and my slope is 2. So let's graph that. My y-intercept is 5. I'm going to come up to +5. If my slope is 2, it means I'm going up 2 and over 1. And so my graph will look like this. I'll just connect those dots. So that's the graph of y equals 2x plus 5. To graph the reciprocal, I'm going to use blue. I know that I have a vertical asymptote where f of x crosses the x-axis. So my vertical asymptote comes in here. My invariant points occur anywhere where my original function is equal to 1. So this spot is not going to change because the reciprocal of 1 is 1, and this spot is not going to change. The sketch from this point, now that we know that the general shape, I can look at when my original function is 2, that this would be half. When it's 4, it would be a quarter, and so I can see that it's approaching this line. And similarly, it's going to approach my vertical asymptote. I can follow the same reasoning in the top part of my graph. At this point, my original function is 3, so it's going to be 1/3. And it's going to get closer and closer to 0, but never reaching. And same idea here. So the blue is the graph of our reciprocal. Example number 3. Graph the reciprocal function of x squared minus 4. So what is the reciprocal function? The reciprocal function is y equals 1 over x squared minus 4. State the non-permissible values of x and the equations of the vertical asymptotes. So again, those non-permissible values or vertical asymptotes come from when our denominator is equal to 0. This is a quadratic function, so I have to solve by factoring. It's going to factor into x plus 2 and x minus 2. So this time we're going to have two vertical asymptotes, one where x is equal to negative 2 and one where x is equal to positive 2. What are the x-intercepts and y-intercepts of the reciprocal function? So our x-intercepts, we are going to let y equal 0. So our reciprocal function then would be 0 equals 1 over x squared minus 4. Which gives me no x values, therefore no x-intercepts. Which makes sense with what we've been learning because we never actually crossed that x-axis. Let's look at the y-intercept. For the y-intercept, we're going to let x equal 0. I end up with y equals 1 over 0 squared minus 4. So therefore, y is equal to 1/4. Graph function y equals f of x and its reciprocal function. Okay, so if we are graphing y equals f of x is the function x squared minus 4. So it's a quadratic function. I can find the two x-intercepts of this function. In fact, we did that earlier, of x plus 2 and x minus 2. So on my graph, this means that it's going to cross at negative 2 and positive 2. My vertex, this is also in vertex form, so my vertex would be 0 and negative 4. So here's my vertex. It's opening up. So my graph of f of x would look like this. Now to graph the graph of my reciprocal, again, where my original function is 0 becomes a vertical asymptote. So I have a vertical asymptote at this point. I have another one at this point. And now I can look at points that stay the same. So anywhere where my original function is 1 stays on my graph. As our x values get smaller here, this one's going to approach 0. This one's going to go up. Same idea on this piece, right? At this point, this one is 1. Where this one is 3, is going to become 1/3. As this one is bigger, it's getting closer and closer to 0, so it's approaching this axis. This one is going to approach this vertical asymptote. If we look at our middle section, anywhere where our original function is 1 is going to be on both graphs. So I end up with those 2 points. My vertex is at negative 4. The reciprocal of negative 4 is 1/4 or negative 1/4. And so that point is going to move close to the x-axis. And so our shape becomes like this.